Welcome back to our journey through stoichiometry. In this video, we're going to talk about the yields. Our ultimate goal is percent yield, but to discuss percent yield, we need to know the other yields. So I have them listed here for you. Let's remember what these terms actually mean. Theoretical yield, we've been calculating it. This is anytime you use limiting to find a product. And it's called theoretical because it is calculation only. And it's based on the ratio. It's what you're supposed to make. If everything works out as it's supposed to. Now, the actual yield, as we all know in real life, we don't always get everything out of something that we were expecting to get. So the actual yield is what really happens. Okay, for example, if a farmer plants 50 tomato plants and 45 of them actually make tomatoes, 5 of them die, so his actual yield would be 45, not the expected 50. So actual is what really happens. And that's the case. It's not something that we can calculate. It's only something that we can measure. You go to the lab, you run the experiment, and you calculate with mass, volume, whatever you use to measure, how much of the product that you make. You'll recognize the actual yield because it is typically given to you in the problem. Since it has to be lab-based, you have to be given that information in the problem. So the percent yield really is just a measure of how successful a reaction is. We have a little equation for that. I'm going to call percent yield, give it kind of this symbol here, percent yield. It is equal to the actual over the theoretical. So that would be going back to our tomato plants. If he planted 50, he expected to get 50, but he only got 45, then he would be 45 over 50. And then you convert that into a percent, which in that case would be 90%. So it was a 90% successful job of planting for that particular farmer. I think you're going to find these problems to be really easy, but let's go through a couple of examples together. In example 1, a reaction with a calculated yield. So calculated, that means it is theoretical. Produced 7.89 grams of product. So produced, that's a verb, so that means that's what was actually done. What is the percent yield? Well, as I showed you in the formula, it's really pretty simple. Actual over theoretical. It's grams for each. Turn it into a percent. And in this case, it came out to be 85.5% yield. So one skill that you're going to have to obtain to master this is be able to read a problem and through context clues figure out your theoretical and actual yields, similar to what I did as I read this problem to you. That comes with practice. Now before I go to example 2, let me address the question that may be in some of your minds. 85.5%, many of you are wondering, is that good or bad? Well, chemical reactions have a wide range of possible percent yields. Some of them, like combustion reactions, tend to go nearly to 100%, so they'll be in the high 90s. But there are lots of reactions, especially in organic chemistry, to make things like pharmaceuticals, the medicines that you take. Those reactions would typically have somewhere around 60% yield be considered nice, Some of the more difficult reactions, the specialty chemicals, the ones you pay more for, they're going to have lower percent yields, and that explains or helps explain why those products would be more expensive. So the answer to the question is there's a wide range of percent yields, and very few of them are in the 90s in real life. Let's move on to example 2. 9.87 grams of ammonia is reacted completely. So we're going to use that to mean that ammonia is the limiting reactant. According to this equation, you can see the equation there, if 13.74 grams of urea are produced, so there we go again, are produced, that means this is actual. So our job now is to calculate the theoretical yield. We do that just as we've been doing since we started this unit. Begin with your limiting reactant. Convert it into moles. So 1 mole of ammonia is 17.03 grams. So that's our prep. Let's do our stoich. 1 mole of urea is in ratio to 2 moles of ammonia. So that's my stoich step. And then let's polish it off. Every mole of urea is 60.06 grams. So we'll make 17, or supposed to make 17.4 grams of urea. And this is my theoretical yield. Calculate the percent yield now. It's very simple. Let's take the actual yield given to us in the problem, 13.74 grams. Divide that by 17.4 grams of the theoretical yield, convert it into a percent. This reaction had a 79.0% success rate, or percent yield. All right, as we move now to example 3, I'm going to let you work through this one. It's not that much different than the previous problem, so it should be very easy for you to follow. But you've got a reaction here. The molar masses are given to you. Calculate the theoretical yield of aluminum chloride from 10 grams of aluminum in 3A. And then for part 3B, you're going to find that percent yield. So hit pause now. Work through this problem. When you come back, I'll have the answer posted for you and you can check your work. All right, here's the answer. Let's see how you did. Now for 3A, to find that theoretical yield, we had to start somewhere. We weren't told that aluminum was limiting just straight out. We had to assume it was limiting. From the context of the problem, we were only given information about the aluminum. So we start there. We have the prep to get it into moles. We have the stoich step, and then we have the polishing step to get it into grams. I knew to do the polishing because I did read ahead a little bit, and I did notice that the actual yield was given to me in grams. So that told me, or at least suggested to me, I can go ahead and polish the theoretical yield off into grams. And then once I did that, in part B, we just plugged into the percent yield equation, 76.57%. Like I said, pretty straightforward, but if you do have any questions, we've got some upcoming practice. Come by and see me and we'll work it out.